Okay, so good evening. This is the second tutorial session on the foundations of wavelets and multi-rate digital signal processing. And we'll continue our discussion with what we had started in the last session. Right. So in the last session, we had introduced about wavelets and also with a brief introduction so as to motivate why we are doing it. Then we also had discussed about uh, some of the differences, or some of the most fundamental differences between Fourier analysis and wavelet transforms and the need for wavelet transforms. And eventually we ended with what are some of the mathematical preliminaries which which are the basis for the to understand wavelets. So some of the linear algebra fundamentals, because essentially we require things from linear algebra as well as functional analysis to be able to fully grasp what's going on in wavelet analysis. And so continue with our discussion. And today we'll just take a look at what was discussed in the week 2 of this lectures as per the instructor, what was discussed in the class by the instructor. So we essentially began with what is Haar wavelet analysis. Right. And as we recall, so Haar wavelet was was a function with whose structure was like this. Right? It takes the maximum value of 1, minimum value at -1, and is of unit length along the parameter direction. So there's t-axis, so there is half and there's 1, right? So this is what we call as Haar wavelet, and this is the first oldest wavelet, so to speak. I mean, the first wavelet that was, so to speak, formulated by Haar, who actually began this field of wavelet analysis, right? So we would want to understand this Haar wavelet analysis is also known as the multi-resolution analysis. Multi-resolution analysis. And as the name suggests, right? So this multi indicates, of course, we are very much aware by now. It indicates multiplicity of something. So these are like multiplicity of, they indicate more than one. And resolution is how much can we peek into, our to the signal, right? So it aims at capturing uh, the features in the signal at different levels of say variations. That's what we can call it. If the variations is very low, or if the variations are very high, then of course we need to resolve the signal in a much finer way, right? And if the variations are very low, then we don't need to have lot many data points to analyze the signal, right? Or we don't require lot many, so to speak, terms in the wavelets to be able to analyze the signal. So that's what we call it as resolution. How much can we resolve? So what is the minimum? Say if it comes to the instrument, then what is the minimum? What is the minimum difference between two successive measurements that can be done by the instrument? And in this case, how much can we, how much further can we go using our wavelets to be able to capture the variation in that signal? So that's what it essentially implies, right? So essence, as had been discussed by the instructor, the multi-resolution analysis indicates that it is some sort of a family of wavelets, right? And as he rightly compared it to as if that the wavelet happens to form a family of families such that the most finer resolutions, right? So it's as if the larger the shell, So the more broader, I mean, the more finer resolution I mean, finer variations in the signal it can capture. And the finer one is this is the least resolved, or maybe the way of putting it is wavelets which capture the minimum variations, right? In that sense, we can call it. And of course, these are for wavelets which capture higher variations, which capture larger variations. And of course, although this looks like a Venn diagram, but you must know that we can go as small as possible and as large as possible, because of which it's not an exhaustive list. It extends both ways, this way and even into, it's as if you can go finer and finer. So it's like a, if you can call it a Venn diagram, that it is some sort of circles within circles ad infinitum, which means it goes on perpetuity. There is no end, right? That's how we have defined the basis here. So essentially what we happen to do is we have some signal. So the idea is we have some signal, say this is our signal, right? What we then do is we break it into parts, and it depends on which resolution of the wavelength we would want to capture, right? So essentially what we would do is we just break it down into several components, and let's call it to be, say, t is equal to 0, t is equal to 1, then it was t minus 1, right? So then we would represent this as some sort of a piecewise constant function. So this one will be some piecewise constant. This is also piecewise constant values. So we can call this C naught, C minus 1. Minus 1 is this subscript, and here it will be C naught, right? And likewise, if it goes, then further it will be C1, all over defined over unit length. So we are using different wavelets to approximate the signal with piecewise constant values, right? So that's what we do here. So then you would ask, but would it imply that we are using lot many signal or lot many wavelets to be able to approximate this signal? The answer is no. We do it with just one wavelet, and we can call it phi of t. We use just one wavelet, phi of t, and we capture it by translations, by translating the signal or by translating the wavelength. Wavelet phi of t, right? With by integer, we just translate on the either side just by some sort of an integer translations. So essentially, what I aim to say that all the wavelets can be just denoted as phi and t is equal to phi t minus n. That's it. So if we approximate, say this signal is f of t, right? Then f of t can be approximated as of, there is some terms, of course, it goes till, say, if it happens to be a very say which has its value over the infinite length of t, then let's assume that, okay, till t is equal to -1, we have certain series. Then at around t is equal to -1, we can have c minus 1, which is the constant multiplier, and then we'll just put n is equal to -1 here, n is equal to -1. So this one will give us, this would simply give us t plus 1, because t minus -1 is t plus 1. Then So this is like C1 would be constant for this entire length. Then we'll have C naught phi of t, right? Because t minus 0 is just t, plus C1 phi t minus 1, right? Again, and this goes on uh, as we add more terms, right? It will just keep on going. So essentially what happens is we use just one wavelet and we just are able to approximate the signal by translations, by integer translations or integer translates of that wavelet and able to approximate the function. So here n is an element of z, okay? And this n will have a value a non-zero, I mean, so the, the value of the approximation will be piecewise constant on the integer levels from n to n plus 1. And here we are using this sort of notation to indicate that in the piece value, n and n plus 1 points are not included. So it's as if you're approximating it, this end and this end does not have any values, right? Likewise for every approximation. So it's as if you don't have the value, this function is discontinuous at t is equal to 0, t is equal to minus 1, t is equal to plus 1. Right? So that's what this symbol implies, that the ends in the interval are not included in the set. Right? And this one is all about, as we had discussed last time, these are just linear combination of the translates. And this is to be noted that it's all happening at one resolution. And after this, we'll be trying to understand what we mean by a single resolution in this case. So first of all, what happens is, let's define this set as the space of uh, which is say spanned by this wavelet phi of t to be such that v of x v naught is equal to xt, such that x is an element of L to R. This implies that it's it's a square integrable function, implying that the integral of the squared of the function over any length is always bounded. And we have x dot is piecewise constant on all. Of course, the endpoints are not included, so n comma n plus 1, and n is an integer. N is just an integer. Right? And it so happens that the values are, we have piecewise constant values on intervals of length 2 to the power minus 0. And you recall 2 to the power minus 0 is just the same as 2 to the power 0, and any number to the power 0 is just 1. Right? So, and that's the reason we had constant values at over an interval length of uh, unit length, right? In more general way, what we can define is, and this is, and the wavelet that we chose phi of t, it belongs to v naught, right? So it's as if you can define v naught to be nothing but the span of. So the way we can define v naught is nothing but the span of this. It's the span of phi t minus n, where n is an element of the space of integers, right? Now, and here what we had referred to, it indicates just one resolution. This is just one resolution. And you will understand only when I generalize this space, the space V naught, right? So let's generalize the space. We call it VM, right? So VM is a space of wavelets and which contains all these um, right, it contains all this xt such that you have x dot is an element of, it's a square integrable function, and x dot is piecewise constant on standard or on all, say it's piecewise constant on in the intervals on all n dot to the power minus m, comma, n plus 1 dot to the power minus m, where the endpoints are not included, where n is belongs to the set of integers. So this is a very general space of corresponding to any wavelet, right? So, and this indicates the resolution at 2 to the power minus 1. Right? So this is how we define different level of resolution. So what we do is, because of the way we have defined, say in this case, what happens is it will resolve like that. Say, just to make you understand, say we had a signal of, and I'll let me just consider signal uh, value, which is defined over the domain. So let's define our unit length. So 0, 1. Let this be some signal. Some more space. So let me just bring it down. And now let's start and let's try to understand what we are trying to say. So this we had started. So here we had denoted it by some piecewise constant signal. Let's say it started from here. Let me use a different color. So it started at here and ended here, right? As we know that this is like C naught. So C naught is the value, piecewise constant value. And this indicates for V naught. Now, if we choose V1, for V1, the unit, what happens is for V1, the interval would be, well, and let's also consider n is equal to 0, right? So let's also consider, sorry. Okay, I think I just picked up a wrong. Okay, so let's fix n is equal to 0, first of all. Right? So that through this we indicate that we are only looking at the interval 0 to 1. Fine. Then what we do is the resolution would be for V naught, the resolution is 2 to the power minus 0, which is given by just 1. And this is what we are doing right now. For V2, V1, the unit, the interval length for approximation would be to the power minus 1, which is equal to half. Right? So in this case, we would be breaking the signal into half for this domain itself, right? So it's still. So first of all, what we would be doing is we would be moving from here to, so there will be one piecewise constant here. And then we would be having one more because, of course, and we had required n is equal to 0 only for this case. But this case, we will have two n's. So one will be from 0 to half, and the other will be from half to 1, right? So which means this will be having two sets, right? So I'll just call it C1 not, and let's call this as C1 half. And you see this signal, maybe I should use a strong color here, this color. This tends to represent this signal in a more accurate manner when you compared with this signal here, this signal. So which means that the red colored segment, red colored approximation, resolve the signal in a more what we call accurate manner when you compare with V naught, right? Now we can go further one step ahead, just to understand. So at V2, so you put here 2 to the power minus 2, right? 2 to the power minus 2, which becomes 1 by 2 squared, which is 1 by 4. Now in this case, what you would require is here we had to go from n is equal to 0, comma 1. In this case, you'll have to go from, it will be this particular interval 0 to 1 will be broken down into 4 sub intervals, right? So in that case, you will have n is equal to 0, 1, 2, 3, because the first interval goes from 0 to 1 by 4. The second goes from 1 by 4 to 1 by half, 1 by 2. And the third goes from half to 3 by 4. And the fourth goes from 3 by 4 to 4 by 4, which is 1, right? So essentially what we are doing here is, I'll introduce a different new color here. Say, let me just pick up this color. In this case, we would be dividing this into 4 groups. And now let's determine the piecewise constant. So you'll have, for this, you'll pick this one. And for this interval, you'll have something close to this. And for this interval, you'll have, say, this. And for this interval, you will have, say, this. Just as an example, right? Or maybe let's put it at the average just to show it. Ideally, it should have been just towards the beginning itself. Let me just put it so just to demonstrate this. Now you see that the segment which is, and this will be V2. What we see is the approximation using this yellow colored or V2 space refines or is closer to the signal that we want to approximate. And just wonder, as we increase the resolution or as we increase M, then we'll be approximating our signal over finer and finer subintervals. And that gives us, that's how we can closely and we can just move closer and closer to the actual signal and be able to approximate it, right? So, and as you recall here, just intuitively here as well, that V naught here can be approximated by signals using V1, or can be approximated by wavelets which belong to V1, right? Because the thing is, all that you need to do is bring this red color down here and this red color also down here, right? So which means that you can be able to approximate V naught using V1, right? So which means that V naught is a subset of V1. And likewise, you can represent V1 using functions or using wavelets derived from V2. Right? So all that you have to do is just bring this to yellow bars closer, and then it's as if then you can approximate it. You could approximate 0 to half using V1, and likewise for half to 1, again you can bring both these yellow but horizontal yellow bars closer enough, and then just you can approximate the second segment of V1, right? So this implies that even V1 is a subset of V2. Now, using this, what we call, as we had learned in maths, what we call as the principle of mathematical induction, we can move a step forward, and then this will be a subset of V3, and likewise it goes till on and on till m is equal to infinity. Of course, we'll never reach it, but yeah. Likewise, in this, on the back hand, on the left hand side, we can just go from V minus 1 will be an element of V0. And likewise, this will be minus V2, and this goes on the left hand side as well. Now, this intuition is named as, although we got it through intuition, we call it ladder of subspaces. And this is an axiom in wavelet theory. It says that if you define a base space, which is V0, you can construct it by refining the wavelets further and further using such finer and finer spaces, right? And likewise, on the left hand side, it goes from -1, -2, likewise to infinity. So you'll ask me, okay, what is V minus 1? So in V minus 1, all that you have to do is, since we already had m here, then here m is equal to -1. So this will equal to 2 to the power -1 minus m is equal to the power minus into -1. So it is 2 to the power 1 is equal to 2. So on the left hand side of V0, we are actually increasing the intervals on which we are having a constant piecewise approximation, right? Okay, so now let's talk about certain things here. So first of all, let's try to understand what if when we move upwards. So when we move upwards, this implies that we are moving on and on in terms of resolution. So it's like we are going finer and finer with higher and higher resolution. Then what happens if you unite or take a union of all those spaces, and we have this VM union. And okay, first of all, we'll define this union where m is an element of integers. Then this spans the entire. As of now, it does not span, because as you recall that when we had tried to say approximate it, we always had these discontinuities, because of which even we can take a union of all these spaces and form a set. However, this set will have several holes, right? Holes in the sense that these limit points, right? These points will not be included, will not have any definite value in the set. So all that we do is take a closure of all that, which means that if there are all these points everywhere, right? All these holes, you just fill it up. And that's how you get a closure of all the, and then you can be able to span the entire L2 space, L2 of R, right? So this is called as closure here. And then what if we move downwards? When we move downwards, in that case, what we do is we take an intersection of all we take an intersection of all m is it is an element of VMs, and all that we find is that it only the net intersection of all the functions just lead us to a singleton set, which where only zero is the member. Right? Right. So this is of course the trivial space. This is a trivial subspace. Right? Okay. So now let's talk about these linear subspaces. The linear space here, right? Now we say that functions f1, f2 till fk right? They span a linear space if any function in the space can be generated by linear combinations of this set. And that is what we have known about what do you mean by basis of any space, right? That you can find the linear combination and then you can get any member in that set. And we had just learned some time back that any function in the space V naught can be written as, say, any function, let's call it just x of t, that summation of n is an element of z, cn, phi t minus n, right? And where phi is the Haar wavelet or any such wavelet, right? Phi can be any wavelet, not only Haar wavelet, right? It can be any wavelet. And the cn was the piecewise constants, right? And n is the integer translates. Right? And that we have been able to show in the we just try to understand it using this graphically, right? Here as well. So coming back, what if we have our approximation at a different resolution, right? So say any space, yeah, any space VM can be similarly constructed. And how do we construct it? So VM is equal to span of phi 2 to the power m t minus n, right? And as you recall, 2 to the power m indicates that, so even in Fourier analysis, the higher the term which multiplies the independent variable t, it indicates that it's able to capture finer oscillations, right? So for example, just as an example, right? Say you have 0 to, say, 1, right? And say we have sine of 2 pi t. So in that case, it will be something like this. Now, when you have say sine 4t, then it will be as if it will first move till here and again repeat it. Right? So this is like sine 4t. And as you go say sine 8t, then it by within this half, I mean say half, uh, say time period of for sine 40, it will have already completed the full time period. So it becomes like that, right? So what you see is that the number of oscillations increase and increase, right? So which means that it's able to capture finer variations. So likewise here, as you have as m increases for this VM, then you are able to capture sharper and sharper variations in the signal, right? And so we can say that phi of t is called the scaling function. And this is in the case of multi-resolution analysis. Right? And now let's talk about some of the, and of course, it's also abbreviated as MRA. Right? Now let's talk about some of the axioms of MRA. Of course, we are just discussing what was discussed in week 2 of this course. So what are the axioms? And axioms, as you may recall, they are also called as the self-evident truths. Right? It indicates that there are some certain things which we have assumed, fundamentally assumed, over which all our other constructions or other or whatever we build, we just build upon those fundamental truths or fundamental self-evident truths, right? So here, what are the axioms in the case of MRA? Of course, the first thing that we had was the ladder of subspaces, which means that we had p minus 1, and of course this cycle goes on the left hand side as well. This becomes v naught, then v1, right? And then you have v2, goes on and on. And the properties that hold is such that, number one, the union of Vm, and M is an element of Z, and this is the square integrable function, right? And it's square integrable functions defined over the real space. And then we have the point number 2 that we had learned, the intersection of all the subspaces leads to a singleton set which just contains the number 0. And then you have the third thing which says that there exists a scaling function. There exists a scaling function which is called as phi of t, such that v naught is equal to span n is an element of z and phi t minus n, right? And the fourth axiom was that phi t minus n, where n is an is an integer, is an orthogonal set, is an orthogonal set. And here we need to just point out what do we mean by orthogonal set, right? So orthogonal set is such that if n is not the same, right? Say for example, you have phi n is equal to phi nt, where n is the parameterized, I mean, just some parameterized index. So it will be scaling function, which is phi, this is t minus n, and say m, this becomes say phi t minus m. No, I should use something else. Let's see, call it TP, phi p. So it becomes T minus P. Then it so happens that the value of phi, say from it be into integer translates, right? So say this is our n, then let this be the signal, and this is n plus 1, right? This point. So let this be 1 to minus 1. And likewise, let this be point m, and then we have m, and this is m plus 1. So the signal will look like with the wavelet will look like something like this. So plus 1 value and minus 1. It takes the values like that, right? Now what you see is from this, what you see is unless n is equal to m, the what you call the integration of phi nt and phi m phi sorry, it's I have used this to be p, this to p plus 1. So the integration of the product of phi n and phi pt over the entire time axis is 0. So which means unless, I mean, I should say is such that unless n is not equal to m, right? This will always hold. And only when n is equal to m will this integral have some value, or n is equal to p. Sorry, I just keep on making this mistake. Yeah. So only when n is equal to p will this integral will have non-zero value. And that implies this is the condition for this is called as orthogonality condition, right? Then the fifth axiom here is states that if f t is an element of Vm, then it so happens that f of 2 minus mt is an element of V naught. For all m is an element of integers. Number 6 is if ft is an element of V naught, right? Then for all n is an element of z, then f of t minus n is an element of V. And these are very obvious things that we don't have to say discuss much further because these are obvious. And we has already learned that higher variations like those space which contains, so to speak, which captures lower variations can definitely be captured by those spaces which contains wavelets which can capture higher variations, right? So in a sense that that's the reason if f of t is an element of Vm, then f of 2 to the power minus mt is an element of V naught. For all m is an element of the integer space. Right? Okay. So now let's try to again revise some of the something called as the vector representation of sequences. Right. So first of all, number one is we can always consider functions or signals as generalized vectors. As generalized vectors. Right? We can always do that. And this implies that what do we mean by generalized vectors, right? So the first thing is what do we understand by a vector? Now in Cartesian representation, a vector is, say, vector v is just a collection of numbers organized in some sort of a column, right? So you have v1, v2 till vn, right? This is what this is a vector essentially. That's how we see it. But provided that's represented in some basis, which in our case is the classical Cartesian basis. Now, as capital N, so the last element here is vn, and this is a vector of size n, right? Size n cross 1 if we go by that. And as n tends to infinity, v actually tends to be a function, right? So that's why you can even consider functions or signals as generalized vectors. And here is where generalization comes. Comes when the number of points in that vector, the number of components in the vector tend to approach infinity, which means that there are infinite points in that vector, implying that, say, if we have a signal. So the way I would say is, let's first have this 0 to say 1, right? So initially we had values of the signal at these discrete points, this, and some uniformly separated points, right? Now, as you bring this uniformly, or as you say, measure or record the signal values at finer and finer sampling, say sampling time, right? So it so happens that these points will approach to zero, the distance between two successive points. So it implies that we are actually, so here we can call it as xn, where n is an index. Now, and of course, at till the last point, the last point is the value of, so this is the t-axis. So the last point will be denoted as x capital N. Now, as n tends to infinity, then it simply implies that the distance between any two consecutive points, discrete points on the time axis, they appear what you call approaching zero, which means that this will have some sort of a continuous function. So initially we would have just the value here, like that, right? At different, we'd have the signal values. Now it will be some sort of a continuous value of the signal. And of course, we can never write x of t in terms of a column matrix. The reason because uh, it's never enough. Like you have infinite number of points between just 0 and 1, which you can never represent in a column vector. Right? So then we had talked about what we call as the connections between functions and sequences. So how we are able to make connections and all. Then we moved on to describing certain quantities or certain mathematical operations defined our signals, right? So the way we had said is, say n infinite. So an infinite, uh, which is countably infinite, dimensional vector is a sequence xn, where n is an element of set of real numbers, I mean set of integers, and n is the index variable, right? And we have a sequence which is a vector, right? So, and each n will have, so that can be said to each n represents some component of the vector, right? And before that, and after that, let's talk about something called as dot product of vectors. What do you mean by dot product? Right? So for discrete signal, if it is say x1n and x2n, then a dot product between these signals is just we can call it x1 comma x2. This is nothing but the sum of products of the individual components of the signal, which means that n is equal to minus infinity to plus infinity and x1n into x2n, right? And if it's a continuous signal and you have x1t comma x2t, then in that case x1 comma x2 is just integral of x1t x2t dt over minus infinity to infinity, right? So that's how we would define uh, the dot product between two signals, any two signals x1 x2, for continuous as well as discrete signals. And from here only we have the concept of norms, right? So whenever we talk about norms, it actually implies it's induced norms, right? Or something like to compute a norm, you have to ultimately resort to what you call as the dot product. So now let's just talk about what we mean by norms. Right? So the way we define norms is that the norm of a sequence, say norm of a sequence xn is such that you can have it's defined as this is equal to, it's denoted as x, right? And we define it as using, of course, the dot product. So it is as if you first take the inner product or the dot product of the signal of x with itself and take its square root. And because of which this is always going to be greater or equal to 0. And the norm of x is 0 implies that x is equal to 0, which implies that every component of x is going to be 0. Right? Then only we can call, only for a 0 signal can we have the norm to be 0, right? And so for real signals, we can define, say, for real signals x1 and x2, n is equal to minus infinity to plus infinity x1 n comma x, right? Fine. And however, for complex signals, we have to slightly tweak the definition of the dot product. So for complex valued signals, and here also we should call it for real valued signals, right? So for complex valued signals, the definite and let's consider it still to be x1 and x2. So the inner product of these two will be equal to summation of n is equal to minus infinity to plus infinity x1 and x2n and the complex conjugate of x2 of n, right? And the way we denote this is by saying that for a general signal now, of course, and general signal, we as we know that the real valued signal is just a special case of complex valued signal where the imaginary part is 0, right? So which means that for a generic signal, you have the inner product of x2 and x1 to be just it becomes x2 comma x1, complex conjugate. Now, before that, let me try to, I mean, let's discuss, let's say, observe this particular facet here. Say when you had real signals x1, x2, and when you took its dot product, then we have x1 dot x2, x1 n dot x2 n, and this is just a mere product. This is just a mere product between any two components of the signal, and you are just summing them. So here order doesn't matter. Order doesn't matter. And if you know what we that multiplication and addition are these two mathematical operations which are commutative in nature, which means that A into B is the same as B into A. Of course, at a scalar level, you should not talk about matrices. At a scalar level, it's A into B is the same as B into A. Likewise, for addition, A plus B is the same as B plus A. So it means that you can just write it as x2n dot x1n, which means that x1 comma x2 is the same as x2 comma x1. However, for complex analysis, this is not the same as x2 comma x1. Just let's try to understand why. So x2 comma x1 is will be in integral, I mean summation from n minus infinity to infinity, and you have x2 of n dot x1 of n, and it's complex conjugate. And you clearly see that at the elementary level or the elementary multiplication operation, they are no longer the same. This as well as this, right? So which means that to be able to get that to be able to relate both these operations, take a conjugate value. So say x2 comma x1 conjugate. Then as you recall that conjugate over some uh, or say conjugate of product, right? It goes to the product of conjugates, right? So which means that you can write it as minus infinity to infinity x2n conjugate dot x1n. This already had a conjugate, so there is a double conjugate, and conjugate of a conjugate gives us back. Uh, it's as if we had not even applied conjugate operation over it, right? Right. Um, so which means that we can call it as summation of n to infinity minus infinity to infinity. And it will be x2n complex conjugate dot x1 of it. And sorry, just x1. And this you recall is the same as the above expression, right? So this is the same as, and that's how where this particular identity comes from, right? And this is also linear in terms of the argument. Let's go to the next page and try to understand this facet. So this was property number 1, and the property number 2 states that it's linear in the first argument, linear in first argument. Right. So how is it linear? So let's have a1 x1 plus a2 x2 comma x3. Now let's expand it in terms of what we had wanted. Considering it as let's first consider it as if it's a discrete signal. Then that we can write it as summation n is equal to minus infinity to infinity, or without even this endpoints, it's already implied from summation operation where it is being what are the limits on the summation operation. You can call it a1 x1n plus a2 x2n, right? And into x3n. And let's say multiply it. So a1, and you can just bring it inside. You have a say larger this one x1 plus sorry into x3n plus a2 x2n x3. And from here, what we can say is that if you are, say, summing something an plus bn, this is the same as summation of an plus summation of bn. And that also holds, right, for this summation operator, because even summation operator is linear, right? So this is linear operator. So which means it allows this. So this property follows from the linearity of the summation operator. So this implies that you can just call it as a1 x1n x3n plus again summation of a2 x2n x3n. Now again recall that a1 is a constant multiplier. It multiplies every term with a1, right? So it is as if, why should you have a1 inside? Right? It's the same thing that either you multiply every term by a1 and then add it up, or just add the entire term and then multiply by a1. So compressing also, if you look at from a computational point of view, this is a better approach, that you first add all these terms, add the product of all these terms, and then multiply by a1 finally. So it also reduces the number of multiplication operations, right? So you have this. Likewise, for this also, you can bring out a2 out of the summation operator, and then you can have, and this again follows from the linearity of the summation operator for us to allow for us to be able to bring a1 out and a2 out of the summation operation. So here you will have x2n dot x3n. So this one was, as you recall, this is something which is familiar to us. So you have a1 inner product of x1 comma x3 plus a2 inner product of x2 comma x3. And that is where this linearity in the first argument holds. Fine. Okay. Then there is one more property of this norm, right? It states that you have this property of non-negativity, which implies that it's positive definite. And in this case, what happens is x comma x, this is equal greater than 0, right? And x is equal to 0 implies only when x comma x is 0. Now let's try to understand this as well. Why not prove this fact? So say you have x comma x is equal to, then of course we know the upper and lower limits for this. So xn to xn. Let's say that this is not equal to 0. So let x comma x is equal to this one, and let this be equal to 0. Say, let this be equal to 0. Even when x of n is not equal to 0 for all n is an element of Z. So it means only for certain x it can be 0, but in general it's not 0 for all the cases. Now, if that is the case, then what we see here is that x comma x is going to be equal to xn whole squared, right? And this is always going to be positive, or at the very least be 0 at the very least. But since we said that it need not be always 0, so it means that it's going to be 0 for all cases when x of n is not equal to 0. Then only we'll have, for all those scenarios, this is going to be greater than 0. But this is giving us the sum to be greater than 0. Then when we compare both, there is a contradiction. So because of contradiction, now this is only possible if x of n whole square is 0. I mean, if even x of n is equal to 0 for all n is equal to z, then this simply implies that x of n has to be equal to 0. So that is why if norm and if inner product or the dot product of the signal with itself is 0, this implies that the signal itself is 0. Right? And therefore, this implies that, of course, the norm of x was nothing but the square root of the dot product with itself. So, of course, whatever confusion was holds for inner product or dot product will, of course, hold for this also, norm also. So, which means that this is equal to 0 only if xn is equal to 0 for all n is an element of the set of integers. Okay. Um, Now we'll talk a little bit about Parseval's theorem, and we'll also do a few solved examples today, just to make some concepts clear. Right? So what does Parseval's theorem say? So what is Parseval's theorem? Right? So given a signal x of t, right? Then what we have to do is we can determine its Fourier transform, or say Fourier transform is denoted by x hat, and its argument is new, right? And new, as we recall from the lecture, is it's a Hertz frequency variable. So it simply indicates it's just 1 by second, right? That's what we call as Hertz. Now, and this we determine this x of nu by taking multiplying with the kernel by projecting it over e to the power minus j 2 pi nu t into dt over the entire time axis, right? And this is called as and many a time in say in engineering we often tend to use frequency, not the hertz based frequency but the angular frequency. In that case, the expression becomes x of t e to the power minus j omega t. And then you have dt, right? And in this case, omega is just angular frequency, right? And then you have omega is equal to 2 pi nu. Okay, so what we have is this Fourier transform pair, right? So let's first we have this Fourier transform pair. So this is what we call as the Fourier transform pair. One is in time and the other is in frequency space. Now, the inner product, say you have two signals at first. Say you have two signals, and it can be complex valued as well. Let's at the outset we assume it to be the generic signal, which can be either a real value or complex. Then in that case, x of t has this x of nu, x, and then y of t. Right? Now, the inner product of x comma y is given as minus infinity to infinity x of t, yt, and dt, right? And this inner product happens to be equal to the inner product in frequency space, and this has to be equal to x hat comma y hat. So it's as if and this one we'll have to write it as minus infinity to infinity, of course, in the frequency when we are this is in frequency, the running variable, and then you have so this it follows from the Parseval's theorem that the inner product between two vectors or two signals remains the same no matter which space do you express it in. Right? So that's what it said. It simply says that x dot y is independent of coordinate system. Right? So this is what was covered in this lecture so far, in this week's lectures so far. Now let's try to do some example problems. And in the next session, we will also start, say, doing some signal analysis using MATLAB and Python. I mean, we'll just we'll try to figure out what we'll use, but we can have a basic understanding in both these tools, right? So there is a very nice tool in Python called as pi wavelets. We can even try to exploit that or try to understand what it does, right? Okay. So let's become some questions. So so the question says that does f of t is equal to 1 by t 0, right? If t is greater or equal to 1, and this is for otherwise, does this function belong to L to R? So that is the question. Does it belong? So at first, what is the condition for a function to become to be in to belong to the set L to R? So the condition is that only if f of t squared integrated over from minus infinity to infinity, only if it is less than infinity, which means that only if this is bounded or say finite, then f of t belongs to the space L to R. Fine. Now let's just try to understand what the signals, the expression of the signal, right? How it would look like. So it says that f of t is equal to 1 by t if t is greater than or equal to 1 and 0 otherwise. So something like this signal, the way if we plot it, so it is t is equal to 0 and this t is t axis and this is 1. So of course we'll have here and at t is equal to 1, f of t is 1. So this is f axis. So at 1, right? And it contains this set at this point. And as t increases and for f decays as 1 by t. So it's means that something like that. So it's that at t is equal to infinity, f of t will approach 0, right? Asymptotically, it will approach 0. So which means that f squared of t, or maybe of t whole square, right? Minus infinity to infinity dt. This can be broken down into minus infinity to 1 ft whole square plus 1 to infinity ft whole square dt. And we recall that over the values of t from minus infinity to 1, f of t is 0. So this is over. So what we have is 1 to infinity, and f of t is 1 by t. So it becomes 1 by t squared dt. And you recall the expression for this, the integral, it has this definite integral as 1 by, I mean, the integration of, it gives us t to the power minus 1 divided by minus 1. and this from 1 to infinity. Fine. Since we have minus sign here, we can either change the limits, change the order of limits, or otherwise just bring minus outside and then put t is equal to infinity. Uh, so t is equal to uh, infinity, right? So let's first write it down as minus. It becomes 1 by minus 1 by t, right? And then this is from 1 to infinity, right? So here we can bring 1 minus outside, and then you have 1 by infinity minus 1 by 1, which is 1. So 1 by infinity actually becomes 0. So you have 1. And this is finite. So which means that f of t does belong to L2 of 1. And that's how we, right? So now let's move to a different question. Say you have a signal, say given, we have a signal, given a signal xn is equal to 3 to the power minus n un, and u happens to be a heaviside signal or unit signal, right? And the way un looks like is, so this is how it looks like graphically. So n is equal to 0, and of course this is the n axis. So from n is equal to 0 onwards, it has a value of 1. And again, n represents is the integer, this one, right? It's the index variable. So you have n is equal to 1, sorry, n is equal to 2, n is equal to 3, 1, 2, 3, likewise. But at all points, it always has a value of 1. Only 4 when n is greater or equal to 0. Right? So which means that now if we find, given the signal, let's determine the L2 norm of the signal. And L2 norm, as you recall, was represented as this, and is nothing but the with here, and then is nothing but the inner product of the signal with itself. So first of all, let's determine the inner product. So x comma x is summation, of course, from n is equal to minus infinity to infinity, xn dot xn, right? And then what we have here is, uh, let's try to break it into two parts. N is equal to minus infinity to minus 1, xn dot xn plus n is equal to 1 to n is equal to 0 to infinity, xn xn. And we recall that over this minus infinity to minus 1, this has the value 0. So 0 into 0 is 0. So we are left with this. And all that we can do is n is equal to 0 to infinity. We can have 3 to the minus n. Right? So this one will be equal to, so inner product will be written as it has, it can be, so n is equal to 0 gives us 3 to the power minus 0 is like just 1 plus 1 by 3 for n is equal to 1 plus 1 by 3 squared for n is equal to 2, and likewise. And you can recognize that it seems like a geometric progression, right? Such that the ratio is, it seems like something of the form ar squared, ar cubed, like that. So a is equal to 1, r is equal to ar by r, ar by a, which is in this case is 1 by 3 by 1, which is just 1 by 3, right? So in that case, and also it's an infinite, I mean, you are summing over an infinite number of terms, or it's an infinite series. So it means that all that we have is, for that case, uh, the sum of infinity is equal to a by 1 minus r. And also the reason, because r is bounded, right? R is less than 0, sorry, less than 1. So then in that case, you have S infinity is equal to a by 1 minus r. So you can just apply that formula here. So we'll have 1 divided by 1 minus 1 by 3. And you have 1 divided by 2 by 3, and this is equal to 3 by 2. Right? So this is how you would determine the expression for this to get the norm of the sequence. Okay. Now, say x1 of t, which is given as cosine tan pi t, and x2 of t, which is given as e to the power minus t squared cosine tan pi of t. So it says that which signal is a wavelet? This is a wavelet. Okay, fine. Now we have to say which one of them happens to be which one happens to be a wavelet, right? Okay. So when we look at the first signal, cosine tan pi of t, it has at t is equal to 0, it has some value, and it will oscillate always between -1 to 1. So -1 is the lower limit. So this is x1 of t. This is 0. However, for the second signal, what we see is it of course has same value of 1 at t is equal to 0. But then because of e to the power minus t squared, so it is as if you are dividing it. It's as if first of all, let's plot what does e to the power minus t squared look like. So e to the power minus 2 looks like it's always of course going to be greater than 0. Then at t is equal to 0, this term is going to be 1, and it's also symmetric about the vertical axis here, and it will drastically reduce to 0. I mean, of course, it will never be 0, but it will be closer to 0 very soon. It will drastically try to decay to 0 very, very soon. Right? And you multiply both these signals. So this is e to the power minus t squared. Multiply both these signals, and that's what we are going to get here. So in that case, because of this rapid reduction, it's going to rapidly die down. So this one, as you recall, cosines and sines have global support. So this has global support. And this one is only defined over certain range. After that, the value is almost close to 0, which we can just neglect, right? So which means this has smaller support, right? Smaller support, which simply implies that it, of course, it's not exactly local, but it is somewhat very small. So you can call this as a wavelet because the global support, the reason of support is very narrow. Right? So which means that the second signal x2 of t happens to be a wavelet, right? Okay. Now let's do a few more problems. So say determine L4 norm of the function which is given here as f of x is equal to x squared 0 x. This is only if x this is less than 1, and this otherwise. Now we have to determine the L4 norm, right? So the way we had defined L4 norm was, so say for example, f, right? L4 norm is nothing but first raise x this signal to the power 4, integrate it over whatever the domain is, and then take the fourth root of this. Fine. Let's first start with what is f of x, 4, integrate it over the space. And what we see is this has a local, I mean, this function is locally supported. And it says that the way it would look like is, it is x squared, like that, like that, only when the norm or the magnitude of x lies is less than 1. So which means that these points are not included. So it's only from here to +1, -1. And this is the x-axis, this f. So of course here it reaches a value of 1. So we can break it down into -infinity to infinity, -infinity to 1, do this plus -1, then -1 to -1 to 1, f of x to the power 4 dx, plus you have 1 to infinity. So this part is of course 0. This is also 0. So what we have is -1 to 1. F of x is x squared, and x squared to the power 4 is x to the power 8 dx. This gives us x to the power 9 by 9 from -1 to 1. So what we have here is 1 by 9, 1 minus -1 to the power 9, since 9 is an odd number, so you have -1, right? So you have 2 by 9. So therefore, the L4 norm is equal to 2 by 9 to the power 1 by 4. This is going to be the solution of our problem. Fine. And let's um, say we have phi t and psi of t to be this is like scaling function, and this is as our wavelet functions. Then it says that then we have to just determine what this can have, what property we can have. So since we have not yet learned this question so far, so we will again tackle this. We'll just keep it in our memory so that we'll tackle this problem, because we have not yet discussed about what is the difference between a scaling and a wavelet function, which will soon appear in due time, right? So before that, uh, now let's do one Fourier transform question. So say you have f of t, which is equal to e to the power minus at is 0, and this is if t is less than 1, magnitude of t is less than 1, and a is greater than 0, and this is otherwise. So graphically, this function would look like it's only supported from -1 to 1, and a is greater than 0, and your a is greater than, so this is as if you are just having e to the power minus a magnitude of t, and so which means it's going to be decaying function. So from here you have, it will reach some value, here also it will reach some value, that's it, right? And this is 1, this t 0. So this is the support of this one. So what we do is let's find this Fourier transform of this. So then it will be capital F omega, this omega, and this is minus infinity to infinity f of t e to the power minus j omega t dt. However, we learned that this integral has value only over a narrow region, right? So because of which, what we can do is we will restrict our the domain of integration over from -1 to 1. And we have my e to the power minus a norm of t and e to the power minus j omega t dt, right? And since we have a magnitude operation here, so we'll just split this into two parts again. Only -1 to 1, and it will power minus the norm of, sorry, the magnitude of t when you have -1 to 0, then it becomes, for t negative, the magnitude of t is just minus t. So it becomes just plus at e to the power minus j omega t dt. Likewise, for 0 to 1, what you have is magnitude of t is anyway, since t is greater than 0, magnitude of t is also the same. So you have minus at minus j omega t dt. Right? And this you can filter, rearrange at minus 1 to 0 e to the power a minus j omega t dt, right? Plus 0 to 1 e to the power minus a plus j omega t dt. Then we use all that properties of integral, right? So here it becomes e to the power a minus j omega t divided by a minus j omega from minus 1 to 0 plus, and in this case it becomes similarly j omega sorry, from 0 to 1. Now let's evaluate both these terms. So the first term is you have 1 by a minus j omega as common denominator, and then you have e to the power something into 0 is just like 1 minus e to the power e to the power a minus j omega, and it's also going to be negative, so negative, correct? Then for the second part you have is again our denominator will be equal to 1 by a to the power a plus j omega, and what you have here is uh, e to the power minus a plus j omega minus, so it should also have been t here, so minus 1. So this is what our expression looks like. And if we say, let's try to expand it further. So insert new, let me just duplicate here and then bring it down. So the expression that we had was is equal to, let me rewrite it, a minus j omega, right? And then 1 minus e to the power minus a minus j omega, right? And then you have minus 1 by a plus j omega, and then you have e to the power uh, minus a plus j omega minus 1. So we can just uh, so we can have 1 by a minus j omega minus 1 by, so sorry, omega here, right? Okay, a plus j omega, and likewise you have minus of so it's a plus here, sorry, it's plus here, then minus of e to the power minus a minus j omega divided by a minus j omega, and it will be plus a plus j omega divided by j omega, right? So this is what we are looking at. Now let's use some of the property of complex numbers, right? So we had z plus, say, given any complex number, given a complex number z, then its transpose is z bar, right? Conjugate transpose. I mean, it's conjugate, so to speak. Conjugate is z transpose. Then you have z plus z. This one is just the what you call real part of z. Right? But of course, since the way our situation is, we would have to simplify at least one. So let's pick up any one. Maybe just simplify this. So you have to multiply minus a minus j omega denominator as well as numerator. So in numerator, you'll have a minus j omega. So it will be a squared minus into minus. So it's like plus omega squared. So here, this real part of this was, so the real part of this is just a by a squared plus omega squared, right? And in this case, the real part is, so here also you see that this is z, and take the whole transpose. And you can clearly see that the transpose of any number, if it's say z1 by z2, the transpose of z1 by z2 is it's as if the conjugate of z divided by the conjugate of z2, right? And that's what we see here. It follows that. So we need to just pick up one and simplify it. Minus a plus a, that I choose this, divided by a plus j omega. Let's multiply both numerator and denominator by j omega, a minus j omega. So what we are left with is denominator is, of course, clearly it's a plus omega squared. And the numerator is, we have to use e to the power minus a. You can bring it out as a common factor. And it's as if you are multiplying e to the power minus j omega, e to the power omega, right? And here also what you can do further, we can simplify it as e to the power minus a, and a square plus omega square is now real part. I mean, we cannot further factor it further, and so here this one will be cosine omega minus j sine omega. This into a minus j omega, right? And when you take a look at this e to the power minus a by a square plus omega square, then what you'll have is you will have a cosine omega, right? And of course this is imaginary, so you'll have plus j squared sine omega omega, right? So you'll have is plus uh, j omega sine squared. So it's like then becomes just minus omega sine omega. And the rest will be some imaginary component. I don't care. We don't care about that, right? So it so happens that the real part is just this. So therefore, f of omega is going to be a by a square plus omega square plus e to the power minus a divided by a square plus omega square, and then a cosine omega minus omega sine omega. And that is what. And of course, we'll have to verify whether we are doing right. But yeah, let's consider it. That's how it is, right? Okay, so with this, I believe we are on the, we can call it, we can end the session for today. And in the next session, we believe, or we'll be discussing further in the about week 3 of this course, which where we'll be talking about the equivalence of functions and sequences, and angle between functions and their decomposition, and also some additional information on the direct sum. Then we'll gradually introduce this the concept of filter banks and try to analyze this Haar analysis, do this Haar analysis filter bank in the Z domain, and both in the analysis as well as the synthesis parts, right? And we will start with some MATLAB based uh, experiments, because I believe it's, although it's easier to learn, but since it may or may not be accessible to everyone, but let's still use it, and right, we'll just try to do some of the operations in in this MATLAB, right? So yeah, I would just close this today's session. Thanks everyone. Yeah.
Thank you, sir.
Yeah, thanks. Yeah. So next time, if you, I mean, do you have any dots today, Subhashish?
Sir?
Did you have any dots by in today's discussion by any
No,
chance?
no, sir, no, sir. It's
Okay.
okay.
So what we'll do is in tomorrow next session we will also do some MATLAB experiments. I believe it's usually helpful to also do some practice,
Yes, sir.
whatever we learned in some software.
Okay, sir.
Okay.
Okay, sir. Thank
Yeah.
you.
Okay. 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 Then.